Okay, we are continuing on here, chapter 15. We've been talking about Ksp, and again, our Ksp is obviously our solubility product that we've been talking about, and it really is still just an equilibrium constant, really for things that are pretty much insoluble. And as we see, essentially they are relatively small values for Ksp. The reactions, as we've been talking about, pretty much always have this form where the solid's always on the left-hand side or the reactant side, while our aqueous ions are always there on our product side. So pretty much your Ksp expression is usually just the products that are there. We still do, obviously, as we talked about, the normal things, take the coefficients as the exponents and all those type of things. Last time, we really kind of focused in on things that really do affect solubility. So even, based on solubility rules that may say that something is insoluble, there are really kind of three factors that can have a pretty good effect on, sort of the solubility of a substance. We talked about the idea of a common ion. And much like the common ion effect that we see with buffers, the common ion in this situation is the ion has to be on the product side, which causes the equilibrium to shift away, and it actually does decrease the solubility that we typically see of that substance if it was just in water by itself. So obviously that's one way in which the solubility of a substance would definitely be decreased if you have that presence of a common ion that may be in there. We also talked about pH. And pH really can affect the solubility of things that, for the most part have either maybe hydroxide on the product side or maybe have H plus on the product side. Again, by adjusting the pH either sort of up or down, it can increase or decrease the solubility. So we looked at one where it was, I think, magnesium hydroxide, and it had like a baseline pH in water of like a 10 point, I think it was 9.5 or something in that ballpark. And again, as we talked about, if we sort of brought that pH below that mark, we would see an increase in the solubility. And again, really in that case of the hydroxide, by dropping the pH, we got to add H plus, and those two guys are going to make water. And what that essentially does is remove an ion on this side of the equilibrium, going to cause the equilibrium to shift to the right, and thus it will become more soluble in that case. Obviously, the opposite would be true if we happen to go above, in that case, the 10 point, whatever it was, 45, and we brought the pH well above that or just a little bit above that. What we would essentially be doing would be like adding more hydroxide in that case. And the opposite effect would happen. We would be adding more hydroxide, which again then would force it back to the left and would actually decrease the solubility of it. So as we saw with pH, insoluble bases are more soluble in acidic type solutions. And again, bringing that pH down, going to shift equilibrium to the right. And insoluble acids are soluble or more soluble in basic type solutions. And again, for the same reason, if you have an insoluble acid, you got an H plus, OH minus, H plus, again, going to basically make water in that case and cause the equilibrium to shift to the right. So playing with the pH, which as you got some experience there the other day as well in the actual lab, it affects the solubility of certain things. And again, that's one of the main reasons why we do sort of the adjustment of that pH in those type of experiments, because really the whole point of those experiments is we want to keep certain ones floating and want other ones to be able to precipitate out in terms of ions. And by adjusting the pH, that's one really nice way that you can also do that. The last thing that we sort of looked at was the idea of actual concentration, and the concentration really of the ions that are floating around in that solution is really important as to whether or not you will actually also sort of see a precipitate form. For example, if something is insoluble, and this is where we use something like Q and compared Q to the Ksp value. And again, if the Q value is greater than the Ksp value, it will kind of shift to the left there and it would make a solid in that particular case. If Q is less than the Ksp, it would shift to the right there and it would become more soluble. So we looked at one with calcium hydroxide, which, based on solubility rules should technically be insoluble, but we really didn't have the right concentration of those ions to actually see the solid form. And that also is a very common thing that happens in the qualitative analysis type experiments. Again, as we talked about, every time you sort of add reagents, you're basically diluting it down. And again, if you're really not careful, you can't get to a position where you maybe over diluted it and you were supposed to see a solid and you may not see the solid. We don't do the general unknown anymore in this class for whatever reason, but that's a very common problem when you would do a general unknown, when you would be started, say, from group 1 to go to group 2 to group 3 to group 4 in terms of those ions, and you kind of carry over the supernate into each of those steps. By the time you get towards the end there in group 3, you've done a lot of addition. So what they usually do in those experiments is they build in a step where you take it basically and plop it on a hot plate and reduce down the volume. And that's basically getting rid of all the water, going to bring up the concentration of your ions in that solution. And that allows you to sort of overcome that problem of sort of adding too much solution. Any questions on any of that stuff we were talking about here? Okay, so I think where we laid up here is at another example here, and one really sort of practical aspect of KSP is an idea of what is known as sort of selective precipitation. And selective precipitation is pretty much what it sounds like. What we do here is essentially selectively take out one ion from solution and leave the other one basically floating around. So very similar to what you do in qualitative analysis. The reason we might want to do that is, for example, a situation like this problem. What is the concentration of silver that's required to precipitate out only silver bromide in a solution that contains bromide and chloride, both at 0.02 molar? So obviously silver and the bromide makes a solid, and the silver and the chloride makes a solid, and that is what's pictured here. And for the most part, if these guys were pretty much in the same test tube together, it's pretty much a white solid for both of them. So you would have a very hard time if you just randomly put the silver in and you made this solid to go, well, I think this crystal is like the silver chloride crystal. I think this one's like the silver bromide crystal. You really wouldn't have a way to determine, what solid is coming out of solution in that particular case. So we can sort of use KSP and the idea of selective precipitation to basically figure out, how much silver we would need to add to, in this case, precipitate out the bromide and leave the chloride basically still floating in the solution. So let's take a look at how we could kind of do that. We could take the KSP values that we see here, and we could write our Ksp expression for the top one, which would be the Ksp would be our silver concentration times our bromide concentration, and that equals 7.7 times 10 to the minus 13. Now, what they tell us basically is, just so we're clear, we got a beaker here or a test tube, and there's bromide ions floating around, there's chloride ions floating around. We want to dump some silver in, like silver nitrate. And again, we want to pretty much just take out the bromide as a solid, leave the other ones floating around. So they do tell us that the concentration of the bromide and the chloride is 0.02. So we actually do have this number right here from our Ksp expression, and we could actually solve for silver's concentration. And if we solve for the silver concentration, we get 7.7 times 10 to the minus 13 divided by the 0.02 molar. And if we do that, we get something, we'll call it like 3.9 times 10, I think that says minus 11 molar. So what does this number pretty much represent? This number here represents the minimum amount of silver concentration that you need to start to see the silver bromide come out. So if we take some silver, we get it up to 3.9 times 10 to the minus 11. We dump it into that test tube or that beaker that has those two guys floating around. We should start to see silver bromide, a white solid coming out. Now, what we want to also know is that enough to take out the chloride at this point? So we could do a similar calculation using the Ksp for silver chloride on the bottom here. Ksp would be our silver concentration times our chloride concentration, and that equals 1.6 times 10 to the minus 10. Again, the chloride concentration is also 0.02, so we could do pretty much the identical calculation. Silver here would be 1.6 times 10 to the minus 10 divided by 0.02 molar, and that will get us I believe like 8-ish times 10 to the minus 9 molar, or a bunch of zeros and an 8 at the end on this calculator here. So that number there represents the minimum amount of concentration of silver that we need to actually start to see the silver chloride come out. So in this case, that number is larger, yes, than the amount of silver that we need for the bromide, which is why the question is worded like that. We'll get the bromide out of there first. So if we were to do this and we wanted to separate out basically both of these things, we would take some silver that's at 3.9 times 10 to the minus 11. We should start to see some solids being formed. We could feel pretty safe that our solid that we are seeing is silver bromide coming out of the solution at that point, because that's way too low to get the chloride out. We could even continue to increase the concentration of the silver as long as we keep it under 8 times 10 to the minus 9, and we will continue to see basically solid come out. At some point, you would imagine that pretty much no more solid will come out as you continue to increase it, or you keep adding it, you'll get pretty much no more solid coming out. At that point, we can probably fairly safely assume that we have now removed all of our silver bromide, or the bromide as silver bromide, and we could do what we do in class there. You could centrifuge it, right? Pour off the liquid, which ideally should just contain at this point just the chloride. And now what you could do is actually take the same silver, but beef up the concentration to 8 times 10 to the minus 9. And we once again should start to see some solid being formed, which we would feel very confident should be at this point the silver chloride coming out of the solution. And we could continue that process, obviously, until we don't see any more solid. And at that point, we have now selectively precipitated out the chloride and the bromide separately from each other, even using the exact same basically reagent to precipitate it. But by knowing the correct concentrations and using the Ksp, we're able to really figure that out. So if we wanted to do this, we need to make sure that we got a silver concentration of 3.9 to the minus 11. But we want to keep the silver concentration less than 8 times 10 to the minus 9. Again, that's going to keep the chloride still in the solution at this point. Any questions on that? Yeah. Yeah. Yeah, so you'd have to do some dilution of something like, say, silver nitrate or something like that, you know, if you needed it in that sort of realm. You know, in terms of an experiment kind of like what we do, we don't really have to worry too much about that, because we would probably take both of those out together, and then at that point find a different way to do that. Again, you could probably adjust it, but if you needed to, you would have to do a pretty good dilution of something like silver nitrate. Obviously, you would want the silver in some type of soluble form that would be able to do that. Other questions? Yeah. Yeah. Yeah, in a sense, I mean, it depends on, so if your question is, will it always work out perfectly like this where they don't kind of cross over? There probably will, for the most part, be a range where you could keep one at a certain concentration, the other one at another concentration, and they will kind of separate out. it's, I guess, theoretically possible. They're all very, if you have a very close KSP, you know, they may be, you know, relatively close in terms of the concentration. The other thing you could also do to play with that is you could also start with, you know, different amounts of the ions that are floating in there. So in this case, both happen to be the same. So if you had something that had a relatively close KSP, you can maybe start with a higher concentration of one ion versus the other, and that will give you a little bit more lead room in terms of how you can kind of selectively precipitate out. Yeah. Now, the question did ask, obviously, about bromide coming out first. If the question didn't ask about bromide coming out first, how could we determine that we would expect bromide to come out first in this case? Yeah. Yeah, it would be the KSP in this case, and we can compare it in this case. Remember that there is only one place where you can directly compare the KSP, and that is in a situation where both of these guys produce the same number of ions, right? Because it basically gives us the same S squared, basically, in this particular example. So because both of these guys actually do produce the same number of ions, we could look at the KSP value, and what we actually do see is the silver chloride has a higher KSP value, and that means it actually has a higher equilibrium value, right? And that means we should expect more products, which is aqueous ions. So we should expect it to be more soluble than the silver bromide here that has a smaller KSP and would have a smaller solubility or be more insoluble faster than the silver chloride. So in this case, you know, if it didn't ask that, like it would just ask, you know, how much silver do you need and which one should come out first, this is the way you could kind of check it. Remember, though, that if they do break apart into different numbers of ions, you actually have to do the calculation and then compare it. But here we can directly compare the KSP to help us determine that. Questions on that? So this is a really sort of good aspect of KSP and usefulness of KSP, and using that and using like the KSP with acids and stuff like that. That is how we know in certain experiments, like, hey, you need to drop it to like a pH of like 0.5 to get the right amount of H plus in there to allow precipitation to occur. So that's a very useful practical aspect of KSP. We are doing qualitative analysis, and we did group 1. They skipped group 2. Look at you guys. This is normally what we use in group 2, which is hydrogen sulfide gas. We use ammonium sulfide here, smelly, stinky. We also use ammonium sulfide or hydrogen sulfide gas there for group 3, which we are currently in. And you're very lucky you don't have to do that. But as we also talked about, though, it is actually the same precipitating reagent for both of those groups. And one of those things that we talked about, which, you know, gives a big difference in solubility, is pH. And it's very acidic here in group 2. That is the one that typically you bring it down to like a pH of 0.5, so very, very acidic. As you can see in what we did this week, it's very basic, right? You kind of open up with a lot of sodium hydroxide. You get those hydroxide solids that come out and so forth. So it's a very basic one. So just that difference in pH allows the group 3 to stay in solution while the group 2 guys really precipitate out. Group 4 and 5 are pretty much soluble in most things. So we do get a lot of flame tests. These guys have solubility in everything, but there are still a few that will still make some solids, like barium and calcium. You can make some solids with some sulfates and stuff like that. So there's a few of those guys. But, you know, normally we used to do all these groups. Now we just do 3 and no general unknown. So that's a good deal and stuff. That's usually what you look like when you're doing it. Yes. This is group 4 and 5, which is the fun one. You call your friend over and go, do you see the purple? I don't know. I don't see the purple. Maybe there's purple. So purple potassium is a really tough one, along with sodium, as we'll talk about when we get there. I think we still do that test. The sodium flame is a really bright yellow flame. It almost looks like just the flame when it's lit, if it's not really a nice tight blue flame, you know, it's got that yellow kind of coming through it. So because the sodium flame is really, really bright, it oftentimes will sort of mask the potassium flame. So in like 200A, you did flame tests, right? And they had like the cobalt glass. You would use that cobalt glass to sort of screen out the sodium flame so you could see the potassium flame. And that happens a lot in group 4, again, because we hit things that are really, really soluble and everything. So kind of the only test you could do is flame test, which obviously if you've done flame tests before is sometimes very difficult to determine, you know, what you got going on there. Any questions on KSP or any of those calculations? Okay, so we're going to talk about one more K here because we don't have enough, and that is the equilibrium constant for complex ions. Complex ions are oftentimes metals, a lot of times transition metals that have what are referred to as ligands attached to it. Ligands are Lewis bases. So you remember Lewis bases are things that, what is a Lewis base? Well, it's Lewis, so it involves electrons. And those electrons are being donated over, yes? So a Lewis base is something that will donate a pair of electrons to a Lewis acid, which is usually electron deficient, positively charged. Hence the metal in the middle that has a positive charge, electron deficient, right? So they donate those electrons over to it and they make these complex ions. At some point, we will learn how to name this guy properly. And excuse me. And, you know, you'll get like tetrachloral cobaltate 2. You'll be able to name that just like that. It'll be fun. Good times have by all. So these guys will form complex ions, and we get this sort of equilibrium that sets up here between the cobalt and the ligand. And we can write an equilibrium, which is our products over reactants. This is known as Kf. Kf is the formation constant for a complex ion. It is really just an equilibrium constant. And much like most K values, as the Kf increases, so does the stability of the complex ion. And that's because the complex ions on the right-hand side of the arrow are the product side. So obviously, the larger the Kf, the more products we have, that is the formation of a complex ion. Things definitely, unlike KSP, things want to form complex ions. As we will see shortly here, Kf values are usually super large values. So unlike KSP, where they're like very, very small, the formation of a complex ion is usually very much favored, and we see very large values. We actually saw this occur, this idea here occur in group 1 when you were doing your silver test. You made silver chloride, which was white, yes? You added some ammonia, and the solid went away, right? And it made a complex ion with ammonia. The silver and ammonia made a complex ion where the silver is now floating around the solution. Took it from a solid back to a solution. You added a bunch of acid at the end, which then brought it back out of solution. And the formation of that complex ion is very, very much favored. These ligands actually do come on one at a time. So ligands are added to the metal basically at one at a time, and they each set up an equilibrium. So the first thing that would happen in this particular case is the cobalt would pick up a chloride, and we would make COCl plus, and this would have a K value associated with it. The next thing that would happen is the COCl plus will pick up another chloride and make COCl2. This also would have an equilibrium constant. This COCl2 would then pick up a chloride and make COCl2 minus, and also an equilibrium constant for that step. Last step that would happen is this guy would then finally pick up, I believe I missed one there. That should be a 3. That should be a 3. This guy here will then pick up one last chloride, and we will end up with our guy over here that has a K value associated with it. So ligands come onto the metal in a stepwise fashion. Each one is sort of an equilibrium process that occurs, kind of like how the hydrogens come off one at a time. So it's very similar to that. That, by the way, is how we get the overall reaction there. We add these 4 guys together. This cancels, this cancels, this cancel, leaves us with the cobalt plus 1, 2, 3, 4 chlorides. Make my COCl4. The Kf from this can be found by doing what with all those equilibrium constants? We need to multiply them all, yeah? So if this was like K1, K2, K3, K4, K1 times K2 times K3 times K4, yeah? So sometimes in these problems, you're given it kind of like a stepwise fashion where you might need to add it together and multiply the K values together. Or sometimes you're just given the overall sort of process where all the ligands have basically been added. Any questions to that there? These are, as you can see through my scribble there, different cobalts. They both are cobalt too, but they actually have different ligands attached. Water is a very good ligand because it's a polar molecule, and then obviously chloride is a polar molecule, has extra electrons. So these are some examples of some common ligands. These are what are referred to as monodentate, which means they basically attach one time per molecule. So if you had something like our cobalt there, basically it's just attaching through the oxygen there in the water molecule. Something that's known as basically how many atoms are directly attached to the metal, that is what is known as the coordination number. So this is a cobalt with 6 waters attached. Each one attaches in one place. Coordination number is 6 for that. This is a chloride, which also attaches in one place. And there's 4 of them, which means that it is 4. Now, sometimes people think, well, it's always the kind of guy on the parentheses there. So if we did like coordination number here is not 2 in this case, actually. It is actually going to be 4. And that is because of the actual ligand that is there. This is actually oxalate, I believe that's what they call that. And if you draw oxalate, it looks something like this. And it is those negatively charged oxygens that combine to the copper in this case, 1 and 2. But we actually have 2 of these oxalates. Which this guy could also bind 1 and 2. And it has directly bound to the metal 1, 2, 3, and 4, which is why the coordination number here is actually 4 in this case. So as we'll learn in a later chapter as well, there are certain ligands that are monodentate like the ones that are listed. Oxalate is a very common what is referred to as being bidentate. It can bind in 2 places per molecule, so you get like double the coordination number per molecule. So don't always think it is the guy there unless it is obviously monodentate. I would say oxalate is a common one. You also see one that is known as EN, that's also bidentate. That's ethyl endodiamine. It looks something like this. It has some NH2s going on there. And at each of the nitrogens, it's able to bind to a metal twice per molecule. And that's ethyl endodiamine. It's oftentimes abbreviated just EN is basically the common abbreviation for it. So there are certain ligands that can bind multiple places. There's certain ligands that can bind in a lot of places like EDTA. That could bind in like, 6 places per molecule or 9 places per molecule. And they're really good, as we'll talk about, metal chelators. They basically can grab around a metal and tie it up really, really well. But if you look at a lot of ingredients on certain things, you'll see something EDTA, and it's like used as like obviously to chelate and grab up metals that are in certain things. All right, so let's take a look at a problem that we have here with a KF. And we're going to go through this one together. A 0.2 moles of copper 2 sulfate is mixed with a liter of 1.2 molar ammonia solution. What is the concentration of basically free copper 2 that is there at equilibrium? So for this particular one, we're just going to assume that everything is sort of 1 liter. just to keep everything fairly simple here. So what we could do is we could kind of do a traditional sort of ice table here in this setup. We want to kind of figure out really the initial concentrations of each of these guys. So again, we're going to assume 1 liter, which is not always the case, but just to keep the numbers easy. That means obviously all of the copper 2 originally is going to come from this guy, right? Because this is basically copper 2 and sulfate together. So that is really our source of copper 2. And basically we got something like 0.2 molar. If we take 0.2 moles and divide it by 1 liter, right, gives us 0.2 molar as our initial concentration. And then obviously we'll just assume here we got our 1.2 molar. So if we set up this equilibrium, we have our copper 2, I think it was, plus 4 NH3, making our complex ion of Cu, NH3, 4, and a plus 2 up there. And in this particular case, our Kf value is 5 times 10 to the 13. So our Kf there, 5 times 10 to the 13, I think I said right. Yeah. All right. So initially here, our concentration of our copper, 0.2 molar. Our concentration of our NH3 is 1.2 molar. And we'll assume 0 here. So first off, when we look at this problem, and we typically do sort of KF type problems, there are a couple of assumptions that we typically make in these problems which help us kind of solve them relatively easy. The first assumption is when we look at the K value, is it a small value or a large value? It is a really large value. And that means that when we reach equilibrium, we're pretty much all going to the product side, right? That's a fairly big one, considering 1 is considered big, and we're talking about 5 times 10 to the 13, right? So that's super big. So one of the assumptions that we make is because the equilibrium constant is so large that the formation of that complex ion is definitely favored. Now, in order to form the complex ion, what do you need in the middle? You need the metal, right? And the metal is basically the important part here. So the assumption that we make is all of the metal is going to be completely used up to make the complex ion. So we actually are going to use a number here for the change part. And the number is going to be the amount of the complex ion that is there, or the copper that is there, the metal. This would then be minus 4 times 0.2, and this would be plus 0.2. So why did I do a 4 here? Because of the coefficient. So if we did like a traditional ice table with x's, right? I'll just put it underneath. We would do minus x, right? We would do minus 4x, and we would do plus x basically there. So since we're making the assumption that the change should be the metal, and it's going to be like the limiting reagent, we already kind of know what the change is. So we still have to take in, obviously, the coefficient into account. Any questions allowed? That means when we do reach equilibrium here, we're going to get 0 of this guy. We're going to get on that guy there 1.2 minus 4 times 0.2. 0.4. And we're going to get a 0.2 in this particular case. Any questions up to there? Now, you may be asking yourself, isn't the problem asking what is the concentration of copper at equilibrium? And that is the question. And if we always make that assumption, then we should always end up with 0, and it's not much of a problem at that point, right? If we just put 0 and move on with our life. But we still have to remember that this is an equilibrium, right? Which means even though it is almost 100% heading to the product side, There still should be some that is coming back the other way, right? Because it's an equilibrium. The second part of our assumption is, although almost 100% of it is going to be tied up over there in the complex ion, there still should be a super small amount of actual free copper or metal floating around the solution. So that's sort of the second part of the assumption that we make. So what we're going to do is, even though we sort of zeroed it out, we're now going to really go back and sort of call the metal X, and we're going to solve for it. And that's going to give us how much that's going to be there. And again, it should be a relatively small number. We're going to do that by using our Kf expression, which would be our products. We over our reactants. We also still need to make sure that we take this guy to the fourth in this case. That will essentially give us 0.2 up on top. We're still looking for the copper 2 concentration, and we have 0.4 that we need to take to the fourth, and that will equal 5.0 times 10 to the 13. We basically want to solve for the copper 2 concentration. And if you're not sure math-wise, basically these two guys switch places. It's basically the math there. Multiply the copper to the other side and then divide by the Kf back to the other side. They essentially switch places. And what that will essentially give you is that the copper 2 concentration at equilibrium will be 0.2 divided by 5.0 times 10 to the 13. Divided by 0.4 to the fourth. And if we do that here, we end up with a copper concentration at equilibrium of 1.6 times 10 to the minus 13, and this would be molar in this case. Now remember that the second part of our assumption is that the amount of free metal that's there should be extremely small. Is it extremely small? Yeah, it's pretty much not there, right? It's pretty much all gone, but there is obviously 12 zeros and a 1 and a 3 still floating around in the solution. So these are two really major assumptions that we make when we do these type of problems. The first one, again, being the first assumption is that all of the metal that's in that complex ion should be completely used up. So that will be the change part of your table. The second assumption is, even though it's going to be technically all used up, some of it, like a pinch of it, will come back the other way. And when you do solve for the concentration of the metal, it should be a relatively small value. So if you're doing one of these problems and you end up with a relatively large value for the metal, free metal at the end, something mathematically probably went wrong in that calculation. Any questions on any part of that? Okay, so why don't you try one here, see what you come up with. Calculate the concentration of, like everybody, how much silver, the AgS2O3 minus and the AgS2O323 minus. If you prepare it by mixing 150 milliliters of 1 times 10 to minus 3 silver nitrate with 200 milliliters of 5 molar sodium thiosulfate, and it is the stepwise formation given to you there on the bottom. So take some time, see what you come up with. We're looking for 1, 2, 3 concentrations there when it's all said and done. They gave us the information here in sort of a stepwise fashion. We obviously could add this together and get the overall reaction that's happening by just simply by adding them together. Obviously, this guy and this guy will cancel, and that will give us basically overall, we got a silver that's going to pick up a couple of these guys and will form this complex ion that is over here. Now, if we want the actual Kf for this, we can, if we want to, take each of those and multiply them together. And if you do that, I believe you get a Kf for the overall reaction of 2.9 times 10 to the 13. Now, do we need to use that? The answer is maybe not. We don't actually need to use that number, but you could use that number if you wanted to. The other important thing is obviously we need to do an ice table here. So we do need the concentration of each of those things really in the mixture together. So we are taking 150 milliliters and we're adding it to 200 milliliters, which does give us a total volume here of 350 milliliters when we put it together. And really the obviously only source of silver that's happening here is coming from silver nitrate. So we could get the concentration of silver by really doing M1V1 equals M2V2 in this case. And that basically would be for silver, we're going to take 150 milliliters. We're going to times it by 1 times 10 to the minus 3 molar. We're going to divide it by the total volume, which is 350 milliliters. Again, if you want to convert them to liters, you could do that too, whichever way you want to do it. In this case, you don't necessarily have to because the milliliters here will cancel. And you will end up for silver something like 4.29 times 10 to the minus 4. Or obviously, if you're non-scientific notation, a bunch of zeros there, 3 zeros and a 4 there before it. Any questions on that there? Now, our other ligand in this case is going to obviously be coming from here. This is our source of the ligand. And when that does break apart, we just get basically one ligand and a couple of sodium ions that are there. So we could do the same calculation for that guy, which would be S2O32 minus, would be our M1, which would be 5 molar, times our V1, which would be 200 milliliters, divided by our total volume here, which would be our 350 milliliters. Again, the milliliters will cancel, and that will give us our ligand concentration of basically 2.86 molar. Any question on either of those steps there? So now what we really have here is a concentration really of the silver and the ligand. And we could use the overall equation there to do our ice table. So that is what we're going to do next. So we're going to take really the overall equation here and do our ice table, as that will allow us to get, some of this information that we're looking for here, which is a bunch of everybody's stuff. So let me rewrite the equation on the next page here, which is the overall equation, which is our silver plus our couple of S2O32 minuses, goes and makes our complex ion of our silver and our 2 of these guys, S2O32 and a 4 and a 1, 3 minus. So we're going to use our initial concentrations that we just calculated. So for our silver, it's going to be 4.29 times 10 to the minus 4 molar. We're going to use our S2O3, which is 2.86 molar, and we're going to zero it out here. So we're going to make our same assumption here that the metal should get completely used up. So that is going to be our change as we go across here. So our change will be minus 4.29 times 10 to the minus 4, minus, again, we need to take the 2 that is there for the coefficient and times it by the 4.29 times 10 to the minus 4. And on this side, it would be just plus 4.29 times 10 to the minus 4. Any questions on that part there? That is going to get us a 0 here. I believe that's really going to still give us a 2.86 when it's all said and done. And we will have a 4.29 times 10 to the minus 4 at this point. Any questions on, first off, this ice table? Now, from this very first ice table, we actually hit a couple of things that we were looking for. We have the concentration of really our final complex ion, which would be 4.2. 4.29 times 10 to the minus 4 molar. We also have the concentration of our S2O3 2 minus, which would be 2.86 molar at this point. So it's a couple of things that we were able to solve just from doing, obviously, this ice table here. Any questions on that? So the couple of other things that we are looking to solve for is we are looking for the silver concentration, and we're also looking for sort of this intermediate along the way as well. So there are a couple of ways you could kind of go about getting here. So I'm going to show you sort of both ways. So we'll start with what they gave us in the problem. If we look at what we just got out of the first ice table that we did, we got this guy's concentration here, and we got this guy's concentration here, which means technically speaking, if we wanted to, we could simply use the second equation here to get the kind of intermediates concentration along the way. So we could actually use each of these individual steps because they're equilibrium reactions, they're equilibrium constants. We could use the individual steps to find what we're looking for here. Again, very similar to what we did with the polyprotic acid. We kind of use each individual H plus to kind of figure out everybody's concentration along the way. So I'm going to do that. So what I'm using here is the K2 expression, the equation, and the K2 equilibrium constant. I'm not using the overall reaction here. I'm not going to use the overall K value. I'm actually just going to go back to the second step and use the information that is there, because frankly, I could do it pretty easily. So if I go back to step 2 there, which again is this equation, and it has this K value, which is 3.9 times 10 to the 4. I could just use my equilibrium expression for that step. So if I write the equilibrium expression for step number 2, I'm going to take my products, which is this guy here, divided by my reactants, which is this guy, maybe. Get the thing to right. Try that again. Maybe. Let's see. And my S2O3 2 minus. And that's going to equal my 3.9 times 10 to the 4. Putting my values in for my table, I will get 4.29 times 10 to the minus 4 divided by this guy here, which is what I'm looking for, because that's what it asked for in the problem, and my 2.86 here will equal 3.9 times 10 to the 4. It's going to be basically the same math. The K value and the missing concentration there is going to switch places. And if you do that, again, these guys are just going to switch places. If you do that, that will give you this guy's concentration, which is what we are looking for. One of them, the answers will be 4.29 to the minus 4 divided by 3.9 to the 4th and divided by a 2.86 gives us a 3.8 times 10 to the minus 9 molar. Now, again, I am strictly using step 2's equation, which is why I did not square the bottom guy. Yes, because the squaring happens in the overall equation, and I'm not using that K value or anything like that. It is all based off of this reaction here. So that, again, is why we're not doing any type of squaring of that 2.86 number. Any questions on that step there? Well, we're not going to ignore K1 because now we still need to find the silver concentration. So by doing the second step, if we now go back to the equation, we have now just solved for this guy's concentration, right? And we still know this guy's concentration. So we actually can now go back to K1 and use the first step to figure out the silver concentration at this point. Yes, sir. A silver that would be left over at this point, yeah. Yeah, so remember that, you know, even though it's sort of broken up of stepwise, this is all sort of happening in the beaker, right? So the first step happens, and the second step happens. So when everything sort of comes to equilibrium, you know, based on our overall reaction, what we ended up with, we were basically back calculating to see how much will still be left at that point. Yeah. Yeah. The KF value here? It's by multiplying these two numbers. So as we talked about in the equilibrium chapter, if you add two reactions together to get the K value for the one that you got from adding them together, you multiply the K values together. Other questions? Yeah. You simply, anything that you add them together, anything that's on opposite sides of the arrow that is exactly the same, or they completely cancel out, or anything that's like you got like 4 on one side, 2 on the other, it will reduce down. It's kind of like subtracting. You can think of the arrows as like an equal sign, kind of subtracting to the other side. Then once you kind of get rid of anything that cancels out, everybody on the left-hand side stays on the left. Everybody on the right-hand side stays on the right. So in this particular, I didn't cross it out because we were coming back to them, but basically these guys crossed out, and everybody on the left stayed on the left, and everybody on the right stayed on the right. And that's how we got the 2 S2O3s coming down and the 1 silver. And then what's left on the right-hand side is just the complex ion that's left. Yeah. Yes. I did square it because the calculation we just did was based off of just the second equation, and there's no coefficient here. If we use the K value for the overall reaction and we use the overall reaction, we would need to square it. I'm going to show you that in just a second. Yeah, but that's the real reason is we just use that specific one. So now what we're going to do is use the first reaction step here to get us to the silver. So again, I'm going to focus on just the first guy here, and we'll rewrite the first one. So step 1, which was this reaction, our silver plus the S2O3 2 minus goes to this guy that we just solved for. And this is our K1 value, which was 7.4 times 10 to the 8. So remember that we just solved for this guy. We still have this guy's concentration, which was like 2.8 number. So once again, we could write the equilibrium expression for just the first reaction here, which would be the products of the first reaction divided by the silver concentration, which is what we are interested in this case, S2O3 2 minus. So much like your question here, we're not going to square it because in the first reaction, the coefficient is 1. So we're not using the overall reaction here. That will equal our 7.4 times 10 to the 8. Putting in our numbers, what do we have on that one? 3.8 to the 9, I believe. So that's going to give us 3.8 times 10 to the minus 9 divided by the silver concentration. And again, that top number came from what we just solved for a second ago. And our S2O3 here is still 2.86, I believe. And that's going to be 7.4 times 10 to the 8. Once again, mathematically, these two guys are going to basically switch places. You're going to multiply the silver to the other side and then divide by the K value back to the left. That will give us a silver concentration, which after all this, should it be a large number or a small number? It should be a small number, right? So let's see if we get a small number here. We get a 1.8 times 10 to the minus 18, which I would say is a super small number. So again, our assumption here checks out. Pretty much all of the silver in this case is tied up in that complex ion. Any questions on that? Okay, so now to show you the alternative way that you could approach this, The reason I did all this step by step was because that's sort of what they gave us in the problem. They gave us the step by step. But if you wanted to take the overall reaction, which we had there, which was the silver plus the couple of these guys here, and makes our obviously complex ion that we got here at the end. And we use the Kf value that we originally calculated, which was the 2.9 times 10 to the 13. And that's what we got when we multiplied K1 and K2 together to get it. And if we just go back to our equilibrium line from that very first table that we did, we basically zeroed this guy out, right? We had 2.86 for this guy, and we had 4.29 times 10 to the minus 4 for this guy. And again, that's the equilibrium line from the very first table that we did. If you wanted to, you could have, just like we did previously, hit the silver concentration right off of this equation. So you could have used the overall equation, which would have been this divided by the silver times the S2O3 2 minus, and here would I need to square it? I would need to square it because we're using that equation that we see there that has a 2, and that would equal our 2.9 times 10 to the 13. Putting in our values would get us 4.29 times 10 to the minus 4 divided by the silver concentration times our 2.86 as squared would equal our 2.9 times 10 to the 13. Once again, the silver and the K are going to switch places. And if you do that, you should end up with the exact same silver concentration that we had a second ago. Just to make sure here, 1.8 to the minus 18, yes. So you absolutely could have used the overall equation and went straight for the silver first. If you did that, probably at that point you would come back to the first equation, because at that point you would then have the silver, you would have this guy, and it would allow you to solve for that guy. So you could come back to the first step and get the guy that's in the middle concentration if you chose to do silver first. So there are a few different ways you could kind of approach this. You can definitely use the overall equation. The beauty of it is they're all equilibrium reactions, which means as soon as you know some equilibrium concentrations, you can stick them into any of the steps or the overall step, and you'll end up with the same answer. Any questions on any of those steps there? So again, we still see what we anticipate should happen, that the metal pretty much is 100% used up to make that complex ion. The K value is so large that it is definitely favored. So whenever you get a metal and a ligand near each other, they're going to go after each other and they're going to come together because it is truly really favored. Any questions on any part of that there? All right, last one here to take a look at. We want to calculate the molar solubility of silver chloride in 1 molar ammonia solution. So let's take a look at this together and sort of see how to approach this one. This is actually sort of a combination of both things that we've been talking about. We got some Ksp there. We got some Kf happening here. So we got sort of a combo deal here. We are actually looking for the molar solubility, which means probably the calculation is going to be more like which one? The Ksp type of thing here, right? So we're looking really for S, like when we do our molar solubility. So we can approach this kind of the same way. This is sort of the stepwise fashion that's occurring here. We can actually get our overall reaction just like we did before by adding these together. In this case, it is actually going to be the silver that goes away. It is on the opposite sides. And what we are left with is the silver chloride, which is a solid, plus some ammonia that you're going to add to it. And we're going to get this silver complex ion and some chloride that's still floating around in that solution. Can I get a K value for this reaction? by multiplying these two. Can you multiply a KSP and a KF together? You can actually. They're all just equilibrium constants. Doesn't matter what the little guys on the bottom, they're all the same. That's why we could do, right, KW equals KA times KB, right? Doesn't matter. They're all equilibrium constants. So we actually can multiply these guys together to get the K value. And if we do that in this particular case, we will end up with 1.6 to the minus 10 times 1.5 to, looks like a 7. And I got like a 2.4 times 10 to the minus 3 as our K value here for the overall reaction. Any questions so far? So really at this point, we're looking for the molar solubility, and we're only given 1 molar of ammonia to start with. So as you mentioned before, we are going to kind of approach this like a KSP problem. So I'm going to rewrite my reaction on the next page here. So we had some silver chloride there, plus our, that was a couple ammonias, I believe, right? Yep, a couple ammonias. Making my plus a little bit of chloride action there. And my K value was 2.4 to the minus 3. So I'll stick that over here. 2.4 times 10 to the minus 3. Okay, so taking this like a KSP problem, since we are solving for the molar solubility, we do have an initial amount of NH3, which is the 1 molar. We are going to say 0 of these guys. The change here should be plus S, but not just S, but it should be plus. It actually should be minus on the side. I know my minuses, pluses. It's late and I'm sleeping. Hang on. Let's try that again. Left-hand side should be minus. And this is a little bit different than a normal sort of KSP, as obviously we do have something that we do need to take into account. Minus 2S. This should be then plus S over here and plus S over here on that side. This, technically speaking, is solid, which means we really are not going to do anything with it. Although in the end, we are going to relate it to the silver chloride at the end, but we're not going to do anything with the calculation. At equilibrium here, we will end up with 1 minus 2S, S and S in this case. Any questions on the ice table? Okay. So again, because we kind of comboed a couple of Ks together, that's why it's not like a traditional super KSP problem. We actually do got some stuff there on the left. This is going to go into our equilibrium expression, which will be our products divided by our reactants. And again, here we do need to square the NH3 because of the coefficient, and that will equal our 2.4 times 10 to the minus 3. Putting our numbers in here gives us S squared up on top. Gives us 1.0 minus 2S squared on the bottom is equal to 2.4 times 10 to the minus 3. I got the S squared because this is S and S, right? So we multiply them together, it gives us the S squared. To solve this, I'm going to go with a big square root on both sides. Feels like a good move. That is going to give me an S over a 1 minus 2S is equal to, thing most people forget, including myself, is actually take the square root of that number on the right there. So let me do that. Square root of 2.4 to the minus 3 gives us 4. We'll call it 899 times 10 to the minus 2. We're going to multiply the bottom to the other side. That's going to give us an S is equal to, I'll round it a little bit here, a little too many numbers, 4.9 times 10 to the minus 2 minus 9.8 times 10 to the minus 2, and that would be S. We need to bring the S back to the same side, right, to combine them. So we're going to take that basically plus 1. Gives us 1.098 is equal to S. is equal to 4.9 times 10 to the minus 2. Again, I just brought this to the other side, basically added it back over. We're going to divide by the 1.098, and that will give me 4.9 to the minus 2 divided by our answer, and will give us a molar solubility of like 4.5 times 10 to the minus 2 molar. And that would be the molar solubility of silver chloride in ammonia. First off, any questions on the calculation? Now, let's see if that really is a big deal. If we look at just silver chloride by itself, which I think we have the Ksp value right here, that would give us S squared is equal to 1.6 times 10 to the minus 10, taking the square root of that. Gives us a molar solubility of 1.3 times 10 to the minus 5 molar. That would be the solubility of silver chloride in water. 1.3 times 10 to the minus 5. We just calculated that the solubility of it in the ammonia is 4.5 times 10 to the minus 2 molar in ammonia. Which one is it more soluble in? It is way more soluble in the ammonia, yes? That means you could dissolve 0.04 moles per liter versus being able to dissolve 0.00001 mole per liter of the silver chloride. That is why in that step that you did in group 1, it was this exact reaction happening. You had that white solid, you added that ammonia to that white solid with the mercury. That silver decided, yeah, I want to go over here with the ammonia. It made this complex ion, which was soluble. That's how you got the silver free into the solution while you left your mercury sitting there with his grayish black solid. And then you added the acid, right? When you added the acid, NH3 is a base. That pretty much made all of that go away and re-liberated the silver. And what else is there besides the silver at this point? The Cl minus, which is why you technically were supposed to see the white solid. That was exciting, wasn't it? The white solid come back, and that's why you saw it actually come back there, because of that. So that formation of a complex ion is super. I feel like my thing just died. The formation of complex ion is always favored in these guys because the Kf values are very large. And when those ligands get near those guys, they want to form a complex ion. Any questions on that there? Okay, that is actually the chapter, I think. Yeah.